Yeah.
Okay, I see the live signal. Okay, awesome. Great. Yeah, welcome everybody. Welcome to Weeks of Debugging Can Save You Hours of TLA Plus. So I will contrast TLA Plus to what you usually do if you spend too much time in a debugger. My name is Markus Kuppe. I'm an engineer at Microsoft working on TLA Plus. I've been doing so for about a decade now. So I've contributed to many aspects of TLA Plus over the time. These days, I spend a lot of time training Microsoft engineers in TLA Plus. Perhaps another interesting tidbit here about me is that I once lived in Pune, since this is the distributed systems meetup in Pune. I once lived in Pune when I was a lot younger. You can see still hair on my head. Those days are long gone. And I lived somewhere up here. I think there's the German bakery where I frequently went to. It's a little bit sad that I can only be back in Pune virtually, because otherwise I would have eaten some authentic gulab jamun, which was my favorite treat back then. But I guess has to wait for another day. So anyway, enough about me. Today's talk, the outline is, I will give you the high-level summary of TLA Plus, the executive level summary. This is on slides, and then I will go over, switch to VS Code, and we will debug this challenge 14 that was pasted on this extreme programming wiki probably around the same time that I was living in Pune. And that will allow us to look at TLA Plus. That's kind of a perfect example. We get to meet what in TLA Plus is called safety, and also then the other part of it, liveness, which translates into more technical terms such as deadlock and starvation. And then, if time permits, and since this is a popular question when I talk about TLA Plus, is what about connecting the code to the implementation? And then for those who wish to dig into TLA Plus, I have a homework assignment to get you started, which connects to the challenge we're going to talk about throughout the next hour. Okay, TLA Plus. If you go to Wikipedia and type TLA Plus, then you will see this slightly more verbose version of the sentence here that says, TLA Plus is a specification language to design, document, and verify reactive systems. Reactive systems are systems that exhibit a lot of non-determinism, such as concurrent systems, distributed systems. So they tend to be difficult to get right. But TLA Plus is not first and foremost a formal method. It's it's like it's written here, it's a specification language. And back when the creator here of TLA Plus, which is probably better recognized, more easily recognized by this picture here, Leslie Lamport designed TLA Plus 20 years ago, he assumed that it would be impossible to even write tools for the language. So his goal really was to design a concise language that's precise, expressive, to describe systems. And then it just so happened that somebody went against his advice and implemented a model checker for TLA Plus, which was great, turned out to be great, pretty useful. But first and foremost, TLA Plus is not a formal method. It's a specification language with which we can, like civil engineers, like architects, have something where we can talk about the eventual product, the skyscraper, before it gets built. Also, Leslie wants you to know that TLA Plus, and I can't stress this enough, is not programming. Yeah, we try to abstract the idiosyncrasies of programming, all the stuff we have to deal with when we want to execute something efficiently on a computer. We want to abstract all of this so that the specification really carries the underlying system design. And then also, TLA Plus doesn't free you from thinking. Quite to the contrary, it allows you to better think, to think more deeper about your system, and to catch, so that you catch problems before you actually implement them. So where does this get used? 20 years ago, when Lamport published this book here, the Specifying Systems book, which is still kind of the Bible for TLA+, it was mostly used by hardware engineers. So they picked it up first. But perhaps the most prominent application of TLA+, prominent because it was written about and published in the communications of the ACM, were at Amazon. Around 2014, a number of engineers at AWS designed systems such as DynamoDB. As a reminder, planetary scale, NoSQL database with strong consistency guarantees. So probably pretty difficult to get right. And they started with the kind of established software engineering best practices. Let's have a design document, let's have a design review, let's have whiteboard discussions. Let's write a pen and paper proof to convince ourselves that this stuff works before we really write the prototype. And then once we've written the prototype, we will throw all the testing we can possibly think about at this prototype to really drive up the confidence that the design is sound. And I guess they were a little bit skeptical if this is good enough for the kind of scale that they envisioned. At this scale, at the planetary scale of AWS, even improbable bugs have a tendency to show up frequently. So they ended up looking at various formal methods, one of which was TLA+. So they wrote a TLA+ specification for the systems, and they were a little bit surprised to see that after the system was tested, right, after this prototype was written and all the design reviews had been done, this model checker called TLC found this very subtle bug that required some error handling to kick in, and then something else happened, and then some other error handling kicked in. You can read the paper for more details. It translated into this error trace that required 35 steps. So 35 interactions of the system had to happen for this bug to manifest, to show up. I guess we humans are pretty good at reasoning about 7 to 9 variables. Here we are at 35, right? So you can see this is really, really hard for humans to reason through and get it right. And we need a better language to describe the system, in addition to tools that help us catch mistakes. And in 2014, they then wrote, using TLA+ in place of traditional proof writing, would thus likely have improved time to market in addition to achieving greater confidence in the system's correctness. So this was 2014. At reInvent 2021, which just happened recently, one of the senior directors had a slide again with TLA+ on it. So it's still in use at Amazon. Okay, enough about the sales pitch here, enough about the slides. Let's head over to the interactive part of the talk. The protocol is going to be that I will ask a lot of questions and you have to answer them. And I also want you to answer questions and ask questions. The only real rule I have is that if you want to ask a question, you have to turn on your webcam. If you just want to answer a question, you can just keep your webcam off, that's fine. But if you want to ask a question, please turn on your webcam. And better yet, just turn on your webcam. Because if you've done a remote talk in the last couple of 2 years here, you've probably learned how hard it is to just talk into a screen where you can't see anybody, where there's no audience visible. So please turn on your webcam if possible. Okay, thanks. So let's now head into this tale that I don't think is completely unreasonable. We just pretend our system crashed, right? That happens, and I guess we've all been there, done that. in this particular tale, the DevOps, the site reliability engineers saved the day because they poked the machine, it resumed operations, and everything was fine, right? But there's still this post-mortem to be done to really figure out what the actual problem is. And this is our task. So me and you and collectively, we will get this sorted out, what the problem is, fix this thing once and for all, and then really be sure that we have a reliable system. So what was the problem? Yeah, so site reliable engineering told us, okay, we have this queue here, first in, first out, where a number of producers, P1 to P4, but really can be any number, add elements. And on the other side, these consumers here, C1 to C3, remove the elements again. Yeah, the buffer is of fixed size, gets initialized to a size, and then it stays there. Yet, even with a static number and constant number of producers and consumers, the system ended up in a deadlock state. So none of the producers were able to add elements, none of the consumers were able to remove elements, even though there were elements in the queue. So in other words, we ran into a deadlock. So let's see how this is possible. So I already extracted this piece of code here for us. So I narrowed it down to this particular piece of code here, which is the C implementation of this multi-producer, multi-consumer queue. Let me just quickly give you the intro here. So at the end here, we create a bunch of threads. Okay, we create producer threads and we create consumer threads. Pretty straightforward. We allocate a bunch of data structures like the buffer and the mutex and the condition here. Okay, and then producers will add elements to the buffer and consumers will remove elements from the buffer. So let's look at producer / consumer. So here's producer. In a while loop, each producer will try to add an element. Well, this doesn't always work, right? Because sometimes the buffer is full. Well, then the producer has to wait, right? So we log the internal data structure, straightforward mutex. We check if the buffer is full. If the buffer is full, well, then wait, right? You wait on a condition. Eventually, this producer here will have a chance to exit this while loop, the inner one, and get to here and add an element to the buffer. And then, okay, again, it signals that it's done its work and it unlocks the data structure. Yeah, so this is our kind of critical section here. The consumers, likewise, they lock the mutex. If the buffer is empty, well, then the consumer has to wait. Eventually, again, it will be able to remove an element, the head element from the buffer, after which it will signal that it's done and unlock the system. So producer and consumer, these two functions here, are mutually exclusive because of the lock, right? So how on earth can this deadlock? Theories?
So does the pthread condition wait unlock an entry and lock again on exit?
Yep. So here's the mutex lock, here's the mutex unlock. And then also likewise in the consumer, here's the mutex lock, down here at the end, whoa, is the mutex unlock. So that's not it.
The pthread condition wait function, does it unlock when it's called and lock again when it exits the function?
Yep, it's down here. See, we signal the modify. Well, maybe don't take my word for it. Maybe this doesn't deadlock. Oh, host has not something about being not able to unmute.
I have enabled.
Okay.
And could you try now?
Yeah, thanks. I think I was just getting the same question. The pthread can't wait. I mean, does it release the lock? The function.
This one here. So
yeah.
I mean, well, it does release the lock. So if you wait, then it doesn't. So first of all, let me start and run this run this test case, right? So let me compile it, and let's run this piece of code here. Producer, consumer, and I say, what kind of, how many threads do you want to run it with? Like
just 4 and 3.
Can produce, pardon?
4 and 3, like you're an example.
So in my example, oh yeah, we can run it with, that would be one way. Let me just get started with 10, 10, 10 maybe.
Okay. So
there is some instrumentation here that I didn't show you, okay? So this is what prints the values consumed, values, yada, yada, yada stuff here, every 100,000 elements or so. So first of all, we have to note, it doesn't deadlock immediately, right? And this would also, in going back to our tail from the slides, I mean, the system was obviously running for multiple weeks, if not months, without problems. As always, right? It works for a long time and then suddenly hell breaks loose. So pthread condition wait really lets others acquire the mutex. So if we have a producer here who acquired the lock and then waits, another consumer or producer can acquire the mutex again. That's not the problem.
Sure, thanks.
Okay, we will keep this running here. But thanks for asking. Please keep going. So let's while this is running in the background here, let's look at the TLA plus translation of this algorithm here. And I will give you kind of the, where is it? Oh, here it is. So I will put it side by side. So we will need producer and consumer here. Here is the producer equivalent in TLA plus. It's an action that takes a thread of some sort and a piece of data that's supposed to be added into the buffer. And then we have two logical formulas here that are OR together. So this symbol here, that's an OR, logical OR, right? And programming, you would probably expect this here. But in TLA plus, we like to use the mathematical symbols. And likewise, this hat here, that's the end. So others might recognize this one here. Okay, so the screen isn't very clear for you. Then maybe let me try something else if you can't read this.
I think because the terminal is kind of constantly changing, it's trying to refresh. I think if you can hide the terminal, it may work. Could you please try that?
Okay, let's try that one for a second. And otherwise, I'm going to share my screen if this doesn't work. But good idea. Getting back to this code here or to this formula. So there are two cases here, which happen to be mutually exclusive. If the buffer is not full, right? If the length of the buffer is not at buffer capacity, well, then in the next state of our system, later, it's the value of buffer with this D element appended. Okay, we add the element to the buffer. And we notify, like we do notify over here, although here it's a little bit more technical, pthread condition signal. In the other case, if the buffer is at capacity, yeah, well, then we have to wait. Again, this is abbreviated. It's not named pthread condition wait. This is more in line with what the Java signatures look like, right? Notify and wait. And then for get, consume, it's if the buffer is is not empty. This is the empty buffer here.
Marcus,
The buffer.
sorry
Yep.
to interrupt. The screen is still quite blurred, I think, for a lot of people.
Okay, so let's
you might
switch
want to-
to screen share here. No problem. You just have to allow screen share.
Yeah, doing that. Would you try that now?
Yep. Desktop 1. I hope this is. Oh, share. Oh, now my screen is gone. I can't see you anymore. What do you see?
We're
you
able to see you as well as the screen and absolutely clearly.
Awesome. Perfect. Great. Okay. So get looks like this if the buffer is empty. If the buffer is not empty, in the next state, we remove the tail element from the head element from the buffer and keep the tail and notify. And if the buffer is empty, well, then we wait. Pretty straightforward. Sans perhaps the slightly uncommon syntax. But it doesn't stop here. In TLA+, we just actually describe a state machine. And a state machine always starts with an initial state or a set of initial states and the definition of a state machine, and a next state formula that says, given we are in a state, what are the possible next states? So we have to do this here as well. So this init here says, initially the buffer is empty and this set of waiting threads is also empty. None of the threads are blocked, the buffer is empty. And I have to switch to a different version here. 1 sec. Need another terminal, because this is actually a later commit in the tutorial. Git checkout, let's see, we want to go here. Okay, so this looks a little bit simpler here, great. So initially the buffer is empty and the wait set, the set of all waiting threads is also empty. Over here in the C code, there was no explicit wait set, right? Because this was handled for us by I guess, glibc or so. Okay, and then in the next state, so given we are in some state, what can happen next? Well, what can happen is we can pick any one of those threads that are not yet blocked, right? The running threads. This is essentially all threads minus the ones that are currently blocked, minus the ones in the wait set. And if the one I happen to get from this T here happens to be a producer, well, then we let it do its put operation. If it happens to be a consumer, then we let it do its get operation. Okay, state machine, we start with wait set empty, buffer empty, and now I pick one thread, check if it's a producer or consumer. If it's a producer, I let the producer do its thing. If it's a consumer, I let it do its thing. Also, kind of straightforward, right? And please interrupt me if you have questions, if there's anything unclear here. So the only two things we have to look at now is the definition of notify and wait. Yeah, you ask about p-thread condition wait, whether or not that unlocks the mutex. Here we actually are specific about it. We say a wait operation means simply that we add this thread to the wait set. Okay, whoever is calling wait has to wait because it's now in the set, wait set. And if it's in wait set, it's no longer a running thread, right? So subsequently, it cannot be scheduled by this thing called next that we saw earlier at the bottom. And the notify is, well, if the wait set is not empty, this is not empty here, well, then again, we pick one of those that wait and remove it from the wait set. That's it. Questions so far? So who has questions about the TLA plus formula?
I have a question about the running
Sure.
threads at the top.
Yeah.
Is that a kind of a, I mean, is that a kind of reactive thing in the sense like you specify it once and then that gets computed every time?
You can think about it that way, yes. But this is really, I would say, nothing we want to concern ourselves with right now. Whether or not this gets reevaluated or not really just says, well, I have this expression here that I named running threads. So this equals is not equality like in programming. It just says it's defined to be. Okay, so running threads is defined to be the set of the producers. Cup is the union. So the producers union the consumers minus the weight set. So we take a pot of producers, combine it, pour it into the consumers, and then we remove all of them from this bucket that are in the weight set. This is just it. Okay.
Got it. Yeah, thanks.
No problem. And by the way, good question, because I haven't really said, okay, producers and consumers are two constants. So they're just two sets that don't change over time. There are a few producers in there and a few producers in there. And these don't change, hence constant. Okay. And also the buffer capacity doesn't change. It's also a constant. Okay, can ignore this assumption here. Let's get rid of it. Okay, but I hope you can pretty much see this translation from the C code into the TLA plus specification, how this relates to each other. So let's see if we can, what we can do about it now. I will use this thing, this model checker that I mentioned earlier. So let's check it. Well, it runs, says success, whatever that means. And it says, oh, yeah, I generated 14 states. Okay, so what are those states? Let's rerun this again and dump.bq. So I asked the model checker to generate a visualization here. And I will quickly make bigger. And we can say, okay, here are the 14 states that it generated. Okay, here's the initial state, which is why it's gray. The buffer is empty and the weight set is empty. And then for the system, it's possible to go over here to this state, for example, where the buffer is empty and a consumer is waiting. Okay, so obviously this transition here is a get operation on an empty buffer. And we have another operation here. Okay, so this is another thread that also gets on an empty buffer. And here we have an operation where a producer adds an element to the buffer. And then the arrow that goes back is a get operation by some producer as a consumer. Okay, so this looks all fine. But I guess if we look closely and look at all these 14 states, we will see, aha, there happens to be a deadlock down here. Because down here, all the producers P1, C1, and C2 are in the weight set. And I happen to run this with one producer and two consumers, okay? And a buffer of size 1, I believe. Okay, so there happens to be a deadlock. So let's see. This one is still running, our unit test. That one's still running. Let's try this again with a different combination. I think I said buffer of size 1, one producer, and two consumers. Okay. Oh, now it crashes. Now it deadlocks. And I guess, yeah, this is reproducible now. So let's see, what about this combination here? 1, 1, 1. So this one happens to be fine. So that's strange. So there are combinations or configurations where the system deadlocks, and then there are configurations where the system doesn't deadlock. And if you're unlucky, well, then in your unit test, you pick a configuration that doesn't deadlock. Fortunately, we picked this one here, so we found the error trace, this visualization. Let's blocking queue CFG. Let me remove the second consumer here. And let's check this again. So now it says 4 states. And the visualization looks like this. Okay, that's easy. And it's also easy to see that there is no state where both threads are in the wait set. Okay, so indeed, this doesn't deadlock because these are the 4 states, the only 4 states the system can transition through. And it's exhaustively checking all states, generating all states here. Okay, so now we've confirmed that there's a deadlock and it happens with some configurations and it doesn't happen with others. Let's see, let me check real quick. Cast R. Okay, let me move ahead in my commits here. And so if you run this for a couple of configurations, you can plot it. And this is what I've done with TLA plus. So here you have on the y-axis, you have the number of producers and consumers, the size of this union, right? So it goes up to 8. And here you have the buffer capacity on the x-axis. So it so happens that there is this line here that if you have more producers compared to the size of your buffer, then the system deadlocks. And if you have fewer producers and consumers beyond this blue line, beyond this threshold, then the system never deadlocks. So this is interesting problem, which says with random testing, but also with the model checker here, if you pick the wrong configuration, it doesn't find the deadlock. But at least with a model checker, you systematically can systematically explore this configuration space here and find out where to draw the line. Okay, but we're none the wiser when it comes to the actual deadlock, right? Or does anybody now have a theory where the deadlock is coming from?
Yeah, I think, I have a hypothesis. Let me see if it works. Okay. So I think when you can do a notify, it notifies any one of the threads, not all of them. So I think if all the producers are already kind of waiting, and I'm trying to look at the case the deadlock happened with the C1, C2, and P1, right? I mean, P1 is already in deadlock, and C1 kind of consumed it, and then did a notify, and it went to C1, and C1 kind of also kind of went to deadlock again, right? I mean, did I kind of get a case?
Yeah. You're on the right track. Okay, let's use TLA plus here, do it together. But yeah. Great hunch. Okay. What happened here? It became a little bit more complicated that I wanted to look at. Let's go back here a couple of steps in the material. Symmetry that's get S lock. I guess. One sec. This should be, okay, this is the commit that I wanted. Okay, so far we looked at this graph, right? And then we manually inspected the graph and see if there's a state where the weight set contains all the producers and consumers. That obviously doesn't work well for larger configurations where there are thousands, 10,000, 100,000 of states cannot visually inspect it. But fortunately, in TLA+, we can state a formula that says, okay, this is a deadlock, and we want this to never happen. Okay, so in our case, it is this. The weight set, this variable weight set, should never be equal. So this is not equal here. Could have also written like this, or in programming it would be this, but here it's this symbol. Should never be equal to the union of the producers and the consumers, right? So if we have the union, all the threads, the set of all the threads should never be equal to the set of all waiting threads. If that's the case, we have a deadlock. Makes sense, right? So let's tell the model checker to check this invariant here. And we're going to check it for 3 buffer capacity 3, 4 producers, and 3 consumers. Okay, that should be below our threshold, this blue line that I showed earlier. So this should deadlock. Let's check it with the model checker. And now, it indeed shows errors. There's one error here. Before this was green, right? And it no longer is green. It now says there's an error. And the error is that this invariant that I named invariant is violated. So the invariant is violated. Great. And it not only says it's violated, it also gives us a trace. Okay, so here now we see 47 steps it requires to get to this deadlock, where initially the buffer is empty and there are no threads waiting, to a point where all 7 threads are waiting, and the buffer happens to just contain P1, 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 some data element. And in this case, it just happens to be the name of the thread or the producer. And all the in-between states, it requires to get to this deadlock. So we can rerun this, check again, and again, within very little time, it reproduces the very same error trace, 47 steps again. And no matter how many times I rerun this, it will always find this error trace in a couple of seconds. Okay, 47 is a little long.
Sorry, Markus?
Yeah.
Is this do you recommend trying out, sorry to interrupt you, do you recommend trying out the TLA plus VS Code extension or sticking with the TLA toolbox?
Let's do this afterwards, after the introduction, okay? I have to say something about it.
Okay, thank you.
Let's talk IDEs
because
later.
It looks super cool.
I agree. Okay, so I changed the configuration to the buffer capacity 1 now, 1 producer, 2 consumers. I think we tried that one before, and a deadlock. And actually, let me do 2 producers, 1 consumer, that way around. Okay, the error trace luckily gets shorter. Now it's only 9 states. Well, in the real world, we would now stare at this for a while, right? Read it through, think about it. I said TLA plus is a thinking aid, right? It shows you this error trace, you have to grok it. And that sometimes takes time. But fortunately, let's see, since this is also a demo, I have an animation here for us. Where is it? Let's move ahead. Prophecy variable add visualization. And now, whoever, I have to always open this twice. Come on. Okay, here we go. Whoever wanted to explain the deadlock earlier, I think now is your chance. Now I have the visualization for you. So again, here are our two producers. Here's our consumer, the buffer in the center. You see what the state of the system is up here, the wait set, the set of running threads, and also the thread that's going to be scheduled next in the next event of the system, next state of the system. And I already know that P2 will add n, the element n, into the buffer. So this is all fine. And P2 is active, it's currently executing, right? And P1, which are yellow, are the ones that are enabled, so they can execute, but the scheduler has not yet given control to them. Okay, so n gets added to the buffer. Straightforward, easy. Then P2 immediately tries to add another element to the buffer. This fails because the buffer is full, right? There's this n element in there, so P2 gets blocked. That's fine, because we now have P1 was enabled before, now it's actually executing, so it will probably also get blocked, right? Because buffer is full. Fortunately, we have our consumer over here, C1. It's now C1's turn to remove the element from the buffer. So the buffer is empty again, C1 consumes n. Since it's our scheduler is kind of lazy, if it scheduled a thread, it will keep it running for as long as possible, right? So it's C1's turn again to remove an element from the buffer, but now the buffer happens to be empty. Dang. So C1 gets blocked. Okay, so now we have C1 blocked, we have our P1 blocked here. But P2 is enabled because it got notified by C1, right? Through this signal, P thread condition signal. So P2 is happy to produce the H element and put it into the buffer. It notifies P1 that something has happened, which re-enabled P1. P2, again, lazy scheduler, tries to add another element to the buffer. That fails, dang. And now I think you see that we are already kind of on the path to deadlock and there's no way out. We lost, all the threads are deadlocked. Okay, one more time. Or is everybody happy with the explanation?
One more time.
One more
Pretty
time.
please.
Okay, sure, no problem. Anand, you had the idea. Do you want to try to explain it now that you have a chart here?
Sure. I mean, thanks. So it's what's happening is right now we have these three threads, P1, P2, and C1. So I think what happens is if the thread cannot put anything in the buffer or take anything in the buffer, it would go to block and kind of signal someone else to kind of take over. So that's what's happening here. So we start from let's say I think this state right now where we have both C1 and P1 are already waiting, and the P2 got a chance now. Okay, so what P2 will do is P2 will put an element into the queue and try continuing putting more elements, right? So so it will put H into the buffer now. Could you please move on to the next slide? Yeah, so it has put H into the buffer now, and P2 will try to put one more element, and it will not be able to do. So it gets locked. And what it will do is it tries to notify some other thread to kind of take the control, right? So since C1 and P2 are already kind of blocked right now, only P1 is the one which is ready to run. So it will notify P1, and which again cannot put anything. So that will also kind of go, and that can become deadlock. So
Right.
if there was a way where P2 can actually say like C1, you can actually go and start running, that would have saved us deadlock, but the algorithm doesn't kind of allow us to do that. Did I get it right, Markus?
Right, absolutely. I mean, So we kind of lost at this step here, right? Going from 6 to 7. It so happens that when P2 adds the element to the buffer, it notifies P1. And this was actually the mistake. It should have notified C1. Then if it would have sent the notify to C1, we would have been fine, right? Because then P2 would have tried to add an element again. It would have failed. C1 would have removed it again, and the whole thing would have started again.
It's
Okay.
because the consumers and producers can both be in the same weight set, right?
Well, yeah. I mean, so if you go to the C code, there is no weight set, right? There's just this condition here that we wait on, modify. It's called modify, yeah, and we set the signal. So what would be a fix?
We could have two condition variables, right? One is full and one is empty.
That's the perfect solution. Great suggestion. And in a couple of minutes, we will do that one. Yeah. There's another slightly easier fix, I would say. So what's an easier fix?
Somebody already mentioned, yeah, notify all. Somebody already said it in the chat.
Oh, I see. Notify all. Yep, good idea. Let's let's go back here. Blah, 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 notify. I saw this. I know I have to go next and next again. Okay, next. Okay, so this should be approximately right. So here's our solution with notify all. So who has an idea what the definition of notify all will look like in TLA plus? If we don't get this. Come again?
Set the weight to empty.
Right, exactly. All right, whatever the syntax is, doesn't really matter. Weight set in the next state will simply be the empty set. Right, and this enables all the threads. So let's see if this is a fix. We model check it again, and yeah, it happens to work, right? There are some 1,000 distinct states here, unique states in this configuration. For this particular configuration of, let's see, 4 producers, 3 consumers, and a buffer of size 3. Obviously, now to be really sure, we will probably toy with these values here and see if it also works for other configurations, right? But this was the one that deadlocked for earlier. But you're all very clever people, so you said that's not the best fix, right? Notify all is kind of this shotgun approach. You just shoot at all of them, and then you hit all of them. This animation here kind of made it obvious that you shouldn't notify all the threads, but really just the opposite type, right? If it's a producer, you notify a consumer, and if it's a consumer, you notify a producer. So in the C code, that gets translated, would be done with 2 conditions, right? An empty condition and a full condition. Here in TLA plus, it could look like this here. So I keep the weight set, just one weight set, because I don't want to change out my variables here because I'm lazy. And then I say, okay, I have a notify other operator. And the put here, that's done by the producers. They do notify others with a set of consumers. And the get here, the consumers do notify other with the producers. And what they do is they remove whatever gets given to notify other from the weight set. What remains is the other type, right? Sorry, they do the intersection here, but you could also remove it. They intersect it here, and what remains is the opposite type from which we non-deterministically remove an element from the weight set. So let's see if this works. Yep, also works. Happens to be more distinct states, but that doesn't mean that's less efficient. I would even argue that it's more efficient, right? Instead of doing this notify all and sending a signal to all the threads, now we selectively just send a signal to one of the threads, and we don't get these load spikes. I tried to actually quantify this in a real system, the overhead of notify all and notify other. But yeah, when you look at the C code in glibc, it's too involved to really figure out what's going on. The only thing that I could find out is that the broadcast seems to be implemented by looping over all the threads in the wait set and sending a signal to all of them. So it has to be kind of times the number of threads more expensive. Okay, so that's the deadlock, right? We found the deadlock. We came up with one solution, notify all. Weren't really happy with it, so we went for notify other and discussed how it can be implemented. Could potentially be implemented in C code. So is everybody happy? Let's ship it, call it a day. I mean, I think for you guys, it's a weekend. For me, it's Friday evening.
Not really. I think one of the things is like we had to kind of specify manually in the configuration number of producers and consumers, and we verified that only for that configuration it works fine. Maybe you kind of have another configuration which is still deadlocks. We're not confident of that yet, right?
Good question. Good point. Let's see. Let's change this here to 3, 2, 3. Okay. So that one seems to work, and 2. That one also seems to work. So could now also automate this, right? And run this in some kind of loops where we try out various configurations. I could also rewrite the specification so that the producers and the consumers are no longer constances, but are initialized to some subset of the producers and the consumers. So that's a valid concern. And I would agree with you that if this would be a real system here, we would probably want to do this. Obviously, there's a problem. Say we go to 1024 here and to P3, P4, P5, P. Okay, thank you, Copilot. C4, C5. Okay, so 10 threads of each type and a huge buffer. This now takes forever. Okay, so there's this thing called state space explosion at play here that says that usually if you have a linear increase in the size of your configuration, you just add one thread or so, you get an exponential, most of the time you get an exponential increase of this number of distinct states here. So now after 3 seconds, we are at 1 million states already, and this will run forever. Okay, and then we can't wait this long. Obviously, we can say, okay, if it works for 5 producers and 6 producers, reasonably large configurations, but not gigantic configurations, then this is good enough. And I think in most cases, engineers would actually ship it. I would ship it if it holds for, in this particular case, go to 5, go to 6 of each type. In distributed systems, usually you check your design for 3 nodes or for 5 nodes. And if a bug doesn't show up with 3 or 5 nodes, that's unusual. But I mean, it would be nicer to have stronger guarantees, right? Fortunately, TLA Plus has you covered here. I have to move ahead. Let's see. I think I have to go to the head commit. Get CO main and switch over. Oh, where is it? I have to start. I have to go to a different IDE because the proof system that I'm now going to briefly show you doesn't have an integration for the Visual Studio Code IDE. So we have to use this other one, the Eclipse-based IDE. Okay, let's see. So where is our blocking queue here? So this is let's see. Yeah. So same specification, just a different IDE, right? All looks the same, notify other, and so on and so on. And in addition to what I've done before, I now have two proofs that show that for any number of producers and any number of consumers and any buffer size, this specification satisfies its invariant. Okay, said by this statement, the specification implies always, whatever that means, invariant. And I can re-verify this with the proof system and see this proof goes immediately through. How this proof works, how this proof is done, is a bit too much for us to cover today. Or this part especially is written here. Don't worry, can read it up later offline. The hard part about the proof is not to get this reasoning here at the bottom right. That's relatively easy. What's hard is to get this thing called inf up here, which explains to the machine why our algorithm works. And most of the time, if we design an algorithm, we not always really know why it works. We have a good feeling about it, and we have an idea why it works, but really this so-called inductive invariant is difficult to find. And it's usually too expensive in engineering settings to work on a proof. But if you need these requirements, if you're a safety critical domain, if you want to publish this algorithm, you can do a proof in TLA+. And it's, people do it. Okay, so this system is deadlock free. It's guaranteed to be deadlock free. This is the strongest guarantee you can possibly get for this system. Are we happy now? Do we want to ship it?
Can we please go back to the chart you showed initially for deadlocking system, for which there was some relationship between buffer size and consumers?
Yeah.
Like, I don't have a question, directly any question, but like still not very clear. After I got the explanation about how notification is received by only one of the waiters, but coming back to this relationship, it's not very clear upfront to me how this can be utilized just like that for.
Yeah, I mean, that's something we haven't really specifically talked about, right? Why does this thing only happen to deadlock for these particular configurations? And to be honest, I don't have a good explanation of why it, at least not ad hoc, why it doesn't deadlock for these configurations here. I mean, kind of an informal explanation is that with these configurations, the system is forced to notify a thread of the other type. So a consumer is forced to notify a producer, and likewise a producer is forced to notify a consumer, simply by virtue of how the system configuration looks like. Okay, if that makes sense to you?
Yeah, sounds good.
So, but now with the new design where we have two conditions, two weight sets, or one weight set where we always select the other type, all the deadlocks are gone, no matter the configuration, right? Strong guarantees because of this proof that I talked about. So, want to call it a day or want to keep going? Seems like a trick question, right? So let's see. So the thing that we've looked at so far, this invariant here, that's what's called a safety property. Okay, and a safety property is, in less formal terms, a property that's violated by one particular state. So you have an execution of your system, and then at some point something goes wrong. Informal way of describing safety is nothing bad ever happens. So if a system is safe, nothing bad ever happens. Okay, so what's the system that will never violate its safety properties? So let's say more, figuratively speaking, let's say I task you to build a plane that's not allowed to crash. That's the only requirement I have. What kind of plane do you sell me?
One that doesn't fly.
Right. Yeah. Unfortunately, I probably wouldn't be able to sue you, right? Because my requirements were too imprecise. In a programming, usually we don't have these explicit requirement that something good eventually happens, right? It just kind of implicitly follows from running the system, and then we expect it to do something good. But let's say, for example, starvation, that our system, that every producer eventually produces something. So for all P in producers, always eventually, and I will elaborate on the syntax in a minute, P sub vars. So what this says here, this formula says, for all the producers in this set here, for each one of them, repeatedly, they have to do a put operation. Now, ignore the syntax for now, what the box here means, what the diamond here means, what these other diamond-looking things look like. But the high-level meaning of this is that infinitely many times, all the producers will add elements to the buffer. And we can state this in TLA+. Okay, let's see if our specification satisfies this property. Okay, we already have starvation. So I guess I can remove it up here because I expect that, okay, down here we have starvation already. Okay, and just for now, we just use the first part about the producers and ignore the consumers for now. And let's see what our spec looks like. So let's turn this into spec and not fair spec. So check this model with TLC. And what it says is, okay, here's a system execution where the system starts and doesn't do a thing. Okay, that can happen, right? Because we haven't really told the system to do anything. We've just given the system a specification of what must never happen. Okay, what we now need is this part here, which is a little bit too involved for this workshop or for this talk here. So let me just go back and change the spec formula to fair spec. Redo this again, and we see, okay, with this thing called fair spec, for some reason, our specification works. This is what you can do in TLA+, because TLA+ is highly expressive, but it's not the stuff I want to talk about right now. What I want to talk about is how would you implement something that's fair? So far, we had our weight set here. Where is it? Our variable weight set here, where we non-deterministically removed elements from when we sent a notify. Obviously, you can all see that I could rewrite this specification so that there are also two weight sets, one for the consumers and one for the producers. And that would kind of not map nicely to the conditions, two conditions in the C code. Okay, but how can this possibly guarantee that all producers and all the consumers eventually do something? Because if we just remove non-deterministically and remove an element from the weight set, suppose the weight set is always 2 elements. So we remove one, then immediately another one gets added. We remove one, immediately another one gets added. This could happen. And this one poor guy just sits there forever and never gets removed from the weight set, right? So what can we do? So in where is it? Array blocking queue. So if you look at the implementation in Java, you see that, okay, so this is the put method here. This is the take. They use 2 conditionals, not full, not empty, as I said, like in C, right? 2 conditionals. And they use this reentrant lock. And if we would look at the reentrant lock, it has a constructor that takes a Boolean. If you're familiar with Java, you've probably seen this. A reentrant lock takes a Boolean. This Boolean says whether or not the lock is fair. And the fair lock is one that also has an order of the waiters. Okay, with our set, modeling our weight set here as a set, that doesn't have any fairness because, as I said, a thread could just stay in there forever. But if we would remodel our system now with 2 variables for the waiters and for the producers and the consumers, and with a data structure that has order, contrary to a set, then we get a fair blocking queue here. Okay. It gets slightly changed, slightly amended the specification here, but the only real difference is that the sequences, that we use sequences here for the waiters. So eventually a thread that gets added at the end will travel to the front of the weight set or weight sec and get removed. And this is, again, if you look at Java and the reentrant lock, this is what essentially the implementation looks like. Okay, questions so far? So Jordan, then now let's talk about implementations of this. So this is now the bonus part. Unless you have questions about the previous part, I will carry on. Because one of the questions that I frequently get is, what about the implementation, right? How can we make sure that the C code here or the Java code, I also have Java code of the system here, that it correctly implements the specification? And the answer is, well, there is none, except that we can read the specification and then also read the code. And if you do this systematically and do a peer review, a code review and the spec review, then I would argue that you catch many, many mistakes. And there are companies who apply this technique, right? But it would be nice to automate this stuff to get better guarantees. So one thing you can do, and there are others, but one thing that's also pretty straightforward and easy to understand is, well, one thing that would be pretty easy and pretty great is to just generate some code. Okay, that's kind of the holy grail here. And this is why I mentioned Jordan here, who will do this. Hopefully it will work. We will find out. If you can't do code generation, because in TLA Plus it tends to be that you have a very high level specification that leaves out a lot of detail that's not really relevant for the specification. Yeah, you would have to be really clever. The code generator would have to be really clever. Maybe in 15 years or so, we can have a super smart AI-based compiler. Until then, you probably have to use some kind of templating engine or so, right? Talk to Jordan about that one. Another idea is we can just execute our system, record whatever it's doing, and then see if we replay this against the high-level specification, this might or might not reveal a bug. So let's go back to our producer-consumer input. Okay, so this is our C code again. It's now fixed. It uses now two conditionals, empty and full. And I guess 2 years ago, I gave this talk at a conference and I said, blah, 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 starvation is fixed, deadlock is fixed. There's one problem. When I execute this stuff on macOS, it doesn't deadlock. It deadlocks on Linux, it deadlocks on Windows, but it doesn't deadlock on macOS. I was like, what's going on here? Scratching my head, was puzzled. It was a bit weird because I wanted to debug a system that doesn't deadlock when it should deadlock. But anyway, so I went down this rabbit hole and looked at the definition of pthread, continue, wait, and signal and broadcast and so on. Let's see, I think I have the code somewhere over here. So this is the libc source code that I looked into, and it talks about spurious wake-ups and whatnot, right? I was doing system level programming with multiple computers in front of me, and I was lost. Eventually, I realized what the problem was, because the code that was given to me, it's a bit silly, but the code that was given to me did not initialize the mutexes. So the pthread mutex init calls were omitted. Apparently, that's not a problem on Linux and Windows because they will just do the right thing for you. But here in the macOS world, in the implementation of libc on macOS, this doesn't happen. Okay, so let's see if we can use this technique I talked about earlier. If we can spot this bug here. So I need a shell, cd-impl, let's make trace, I believe. Wait, I have instructions so I don't screw up. Let's remove some stuff here. Blocking queue split trace, okay. So I built the system. I have a little bit of instrumentation in the C code. Okay, so I print the thread that's currently, print the event that's happening, a DQ or an NQ event, a put or a get, right? And that's it. So when I run this, impl producer consumer 343, it writes W for waiter and W for wait, E for NQ, and D for DEC, and then gives some consumer ID, but no producer ID. So I pipe this into a CSV file, out CSV, let it run for a few seconds. Okay, now we have the CSV file with all this output here. And now here it comes. I run our model checker on this specification, and it says it couldn't find the config file. Okay. Oh, models tutorials. Okay, have to be in the right folder apparently. And what happened here? Blocking queue split trace. Huh. I guess this is a demo and nothing. There are things that don't work in a demo. Let's try again. Input out.
Sorry, Markus, could you explain again? So you instrumented your C code to print a CSV file, and then you fed that CSV file to TLC? Right,
so exactly, and I have the CSV file. I can probably open it. It might be too, no, it's fine. It opens fine. It has some 40,000 lines of, 400,000 lines of output. Mm-hmm. So what I now do is I wrote a specification that takes this output and relates every step, every line in this output to the high-level specification of the blocking queue. And then I let TLC check this one. And for some reason, it won't check it. I'm puzzled why it doesn't work. This should have, there's something wrong with the output, I guess. We had it over here. Well, I can later figure it out what went wrong. The idea is, in the demo, before the demo, it worked. Jordan has used this technique, it works. There's something wrong with the file here, I don't know, why it skips over some input, whatever. So the idea is the low-level execution gets checked in terms of the high-level specification. And if they deviate from each other, well, then you know something is wrong.
Oh.
And maybe I know, no, let's try again. Let's try one more thing here before I give up.
So is that because TLC can help you model all the possible valid state transitions that a proper specification has, and then as it's going line by line, if it ever detects an invalid transition, then it says nope?
Yeah, exactly. So, okay, this time it worked. I don't know what went wrong earlier. I think I probably, yeah, I don't know what went wrong here. So we checked the CSV file against our high-level specification, and it says, okay, this CSV file violates the steps from the high-level specification, and this happens after 5 steps. There's one cool thing about it. This plain, straightforward idea you can read about in the paper published by MongoDB, Extreme Modeling. The cool part about this one here is that I don't even know which producer and which consumer executes. I don't care. I just, in the specification that maps the low-level trace to the high-level specification, I non-deterministically just pick possibly one of the non-waiting threads to be the next wait thread. So I use the non-determinism that exists in TLC to make up for this information that I couldn't collect, right? And this is one of the things that was discussed in the MongoDB paper, that they couldn't capture a consistent snapshot of their system. They could have used this technique here, which reflects in that this trace is 5 states long, but TLC actually checked 86 states. Okay, let's see where the slides are up. So, questions?
How many lines of a CSV have you been able to check for a non-trivial specification with TLC reading them and then checking the proper state transitions from instrumented C code or something like that?
Well,
does it scale as well as TLC itself?
Well, that depends, right? Because this one that I just showed you is not just a single sequence, right? But every time there is non-determinism, you get multiple branches here that have to be checked, right? Multiple behaviors. So even if just your CSV file is perhaps 1,000 lines long, if there's non-determinism, it can still translate into millions of states. So the more information you capture about your system, the better it will scale. Technically, just exploring one particular sequence is not a problem for TLC. There's a little bit of cost to evaluate certain expressions, but that's nothing that more compute cannot solve. But I think Jordan has also a little bit more practical experience. So,
yeah. So one of the things that, sorry, I had COVID earlier this week. My voice is messed up. But what we were experimenting with. So we were experimenting with. I gave a talk a couple of years ago at the TLA Plus conference about this. Basically, we built an infrastructure that pushed traces out of TLC into Kafka, and then read them and tried to do basically streaming model checking. But it was hard to find it was hard to come up. It was hard to do check a lot of different types of properties using that approach. I think there are probably some ways that you can handle huge amounts of data by batching it and overlapping the batches and checking batches of like limited traces and things like that. So I think there are ways to scale up even more than just what TLC, the process, can typically handle.
Yeah, right. I think, yeah, I don't think that scalability here really is an issue. One issue that might be is, again, state space explosion in terms of if you do it on the production system that has, again, thousands of threads, then it will become more difficult to find the discrepancies. But again, this is just one approach, right? A pretty low-hanging one because it just takes a little bit of instrumentation. Okay, other questions? Otherwise, I think we're ready to wrap up.
Slightly unrelated question. Like, I just want to kind of understand, like, who uses TLA Plus in the industry? I see like Microsoft and Amazon are using. Are there other people using it, and like how widespread is the use of TLA Plus?
That's a good question. So there's this perception that TLA Plus only works for major companies like Microsoft or Amazon. Well, Jordan here works for a non-major company. They use it. People at MongoDB use it. At safety critical companies in the safety critical space like Thales. There's a LinkedIn group with people from various companies. But even at Amazon, even at Microsoft, it's not that we have hundreds of engineers use TLA Plus every day. It's this tool that you occasionally use whenever you encounter something that's too complicated to just manually read and reason through, right? Even I, who works on TLA Plus and dog foods TLA Plus, so I try to use it as much as possible, I go on streaks where I don't use it, right? Because right now I simply have to implement the stuff. There's nothing that I can use TLA Plus for right now. But whenever there's something that's reasonably complex and that has to be, that I want to get right, I use TLA Plus. And so far, it has always delivered in that afterwards, I never had to go back and fix this algorithm because it was broken. Another way of saying it is multiple times in hindsight, I regretted that I didn't write a specification, but I never afterwards realized, well, writing this specification, this was a waste of time. So it's really, even at the individual engineer, TLA Plus can pay off.
Thanks. I think my broader question is really like, as an independent person not working for a large organization, or probably someone working independently or consulting. I mean, would I even ever get a chance to kind of use TLA Plus? It looks like a very exciting piece of technology, right? I mean, even if I unable to use it anywhere, I'll probably kind of spend time going to learn this, right? Okay, but still, the question is like, will I, as an independent engineer, will I ever get a chance to kind of reap the benefits of TLA Plus? Is that my question in a sense?
Mm-hmm.
Markus, may I interject for a while? So actually, I have one question related to that as well, because I've done some programming on Android as well as with React, not just backend. And that is by default, those systems are multi-threaded systems. So do you have any examples or people doing it TLA Plus? Because especially with mobile, it's very hard to actually even reason about the correctness of data being shown. People don't complain, of course, but I mean, if it works really well, it works really well, but they don't know why it works sometimes. And I really struggled to get it right. I tried modeling TLA Plus, but couldn't continue at the time. But I think if you have any pointers on that, I think that would be great as well.
Okay, yeah. Well, to answer the first part of the question, I would argue that TLA Plus, being a design tool, it makes you a better thinker. It lets you, it teaches you how to think about computations. And even if you don't, so to make this more practical. If I just compare the code comments that I wrote before I adopted TLA+, before I learned TLA+, to the code comments that I write today. This is day and night, right? Because now I have the language, even in prose, I have a way better language and a way better understanding how to think about systems and computations. And this is really the benefit that TLA+ will bring you, or will give you, once you've learned it, that it really helps you as a thinking aid, even if you don't type it out in an editor, what this formula looks like. Maybe I can deflect this question also to Jordan, who has written a couple of specifications.
Yeah, I was just thinking, so the last few weeks we've been redesigning. So I work at Open Networking Foundation. We work on network configuration and control software. So we had this network configuration controller that people had introduced like distributed systems bugs into it and stuff. And so we redesigned it and we wrote it entirely in TLA+ first. And then we translated all that TLA+ in a couple of days over to the actual code. And when we ran it, it just, it worked and we were confused. Like, we were totally expecting to see all sorts of bugs and it just would totally crash, but it worked the first time and it was so weird because it's such a complex system. And so, yeah, it just helps you work. It helped us work out all the problems that we would have run into ahead of time. And then we're just really careful translating the spec. And that's why we're working on, like Markus said, figuring out how to try to use the models, the TLA+ spec to test the code once we translate it. But I think that's going to be a long experiment. So we'll see how it goes.
Yeah, no, I don't think I can stress this enough. The kind of mental mode you adopt after you've learned TLA+, to think in terms of systems, and then you gain kind of a good experience when to model something. Although I think my advice would be always, even if you think you don't have to model something, try and model it. If it turns out to be super easy to write the specification, well then the specification might have been unnecessary. But you learn so much by writing the specification before you write the code that your code will, I mean, I can't guarantee this, right? But I'm glad to say I guarantee that your code will be way better from the start. Rather than patching yourself towards the design, you start with a sound design that you can actually implement. And there are at least a few anecdotes that say, okay, people who've done this approach significantly reduced their code size. And less code, fewer bugs, right? And by the way, if you want to learn TLA+, let's see. So first of all, to get inspiration, we have the examples, like 80+ examples on GitHub TLA+ examples. And you find all kinds of different examples here, mostly distributed systems, but this is distributed systems meetup anyway, right? So you will find the infamous or famous Paxos algorithm here. And there is even a Paxos How to Win a Turing Award. So if you want to find out how Lamport won the Turing Award, you can go read his specification, for which there's also a corresponding talk on YouTube, and understand Paxos through TLA+. But there are also simpler problems specified here in TLA+. A few logic puzzles, and then on this scale between logic puzzles and Paxos, problems of in between complexity. For example, low-level concurrency problems, but also other distributed systems. And where is it here? And then Lamport has a video course, like 11 episodes or so, each one 20 to 30 minutes long. And to be honest, it takes a lot longer to watch them if you learn TLA+. I think after 10 years now, can just watch them in real time and know what he's saying. But if you're new to TLA+, don't be discouraged by spending more time on it. So half-hour video, it's fair to say that probably takes 2 hours or so to watch, to go back and really understand. But it's a great video. He really made an effort to make these grades, and they're also funny. And you learn a lot. If you want to just look at today's material, you can go to this repository here at akka.ms TLA block and queue. And it's organized as a Git repository. You can go back and forth and really look at the diff to find out what's going on, what the differences are between two commits. And there's also prose that explains what the next step is about. And I also recorded a video workshop that I gave last year, which over 8 hours, 10 hours introduces TLA+. Okay, questions?
Hey, I have a question on some related tools. Just wanted to know the differences. So, so this PlusCal, right? How is it different from TL? Is this a subset? Or and the other tool which I have heard about is again from Microsoft called Coyote, which is focused on finding concurrency bugs during runtime using instrumentation. Yeah, just wanted to understand the differences.
Good question. So the first question, PlusCal, you can kind of see it as a domain-specific language for distributed and concurrent systems, which translates into TLA+. So there's a source-to-source translation from your PlusCal algorithm into TLA+. So everything you've seen today, you can also see in PlusCal, except that PlusCal gives a little bit more syntax structures, constructs. So there's a keyword called process. So if you want to define a set of processes, you can use the process keyword to define, yep, this is our process definition here. So when you use PlusCal, it looks a little bit more like an imperative program compared to the TLA+, where it's sometimes, for the untrained eye, more difficult to see. And especially when I write an algorithm or specify an algorithm that I eventually want to implement in an imperative programming language, I tend to use PlusCal for that. Simply because it's kind of closer, and then in the translation I can copy paste chunks from this PlusCal into my Java or C code. And as a matter of fact, there should be, and if you can't find it, feel free to reach out to me. There should be a PlusCal variant of this blocking queue, for example, on the internet somewhere. Okay, and then Coyote. So Coyote used to be P/P#. That's an actor framework where you also get code out. And Coyote kind of targets now .NET as the language to do concurrency testing. They're definitely related, TLA+ and Coyote, but I won't say that if you use TLA+, Coyote is of no use, but I would also not say that if you use Coyote that you don't need TLA+. It's, from my perspective, again, you use TLA+ to get the high-level design right. And then as an aid, when you implement your design, you also use Coyote to get the low-level implementation right. So for example, to give you an example, when I once specified a log-free data structure that I've implemented in Java for the TLC model checker itself, I made this mistake off by one error, I think, or forgot to copy paste a branch of a an if else. And it took me a little bit of time to find the issue. I think a peer review, a second pair of eyeballs would have found the issue. But for this, I would really would have liked to use Coyote, because I'm pretty sure that it would have found the deadlock a lot quicker. I ended up finding the missing piece of code by using a Java-based model checker, which is similar to Coyote. So I think they supplement each other, Coyote and TLA+.
Would you say the same for Alloy 6 that just came out?
I know too little about Alloy 6 and the temporal part. I haven't tried it out to really have an opinion about it. I would love for somebody to write a specification that we have for TLA+, and then we could start comparing it. What I haven't seen, what I don't think exists in Alloy is refinement. I haven't really talked about refinement today, what it is. I think it's one of the less underappreciated features of TLA+, because it allows you, in a nutshell, to do divide and conquer. And if you're serious about your specification, it's a pretty powerful feature. And since this is lacking in Alloy, as far as I know, I would really like to see how well Alloy scales to larger specifications. Not in terms of checking the specifications, but in terms of writing the specification. But Alloy is a great tool.
Cool. So you would say that refinement lets you separate your domain problem into more manageable chunks in some sense?
Well, it's all about abstraction, right? So to give you a more concrete example, and this connects back to Lamport's video course, in this Paxos How to Win a Turing Award lecture, he was at a summer school in 2019 where over 2 days he introduced Paxos. And on the first day, he only discussed the specification that defines the voting. And there's a moment in this video where he says, when I came up with Paxos, I wasn't thinking in terms of Paxos, in terms of message passing, right? How messages go from actor A to actor B, but in terms of this higher level specification that is about voting and consensus. And if you look at this Paxos How to Win a Turing Award specification, you see a high level specification, consensus, refined by a specification called voting. And only this is refined by a specification called Paxos, which has all the details how to send messages from A to B. But to grok Paxos, Lamport uses voting. And he doesn't talk about messages. And this is what's possible because of refinement.
Okay. Thank you. I enjoyed your talk very much, and I appreciate your work.
Thanks. No more questions? Otherwise, I hand it back to the host.
Hey, by the way, a lot of the work that all of the work that we do at ONF is ultimately open source. So we have like tons of the real world TLA plus specs that we work on for our real world SDN controller software. And all the code for that software is online, so it's on GitHub. So if anyone is interested in looking at that stuff, email me.
Yeah, we should add a pointer from the examples to your repository.
Yeah, I think I might have put some of them in there, but yeah, there's also the awesome TLA plus GitHub repo.
You're right. Okay.
So thanks, Markus. So we'll just, have a vote of thanks for joining, giving your time Friday evening, and all the attendees on the call as well on the weekend, and making it a pretty interesting session. So thank you all for your presence and focus. Thanks, everyone.
Thanks for having me. Bye-bye.
Bye-bye.